explain how we got there. So 10 years ago, I was doing my PhD in neuroscience, and I needed to visualize millions of points in 2D. And I had some performance issues because I was using Matplotlib. I tried to find some GPU accelerated libraries, but most of them seem to target 3D, whereas I was really interested in scatter plots and a lot of lines in 2D. So that's how I started to experiment with the GPU and OpenGL for scientific visualization. That led me to release an experimental library called Gallery in 2012. And the year after that, we started to work with Almar, Nicolas, and Luc Campagnola to define a common unified scientific visualization library in Python based on each of our libraries. And yeah, and a few years later, we really reached some challenges and technical difficulties due to the fact that OpenGL was already at the time an old library, as Nicolas said. And since that, VisPy has been maintained by a few people, including David Hose. And in 2015 is the year when Vulkan was announced. And this is really the point where we thought that Vulkan could be really the technology we needed to overcome the difficulties we had with OpenGL. So the first version of Vulkan was released in 2016. I spent the next 3 years trying to understand how it worked because it's extremely complicated. As Nicolas said, it's 1,000 lines of code just to draw a simple triangle. And it's really during COVID that I found the time to really experiment with Vulkan. And last year, I released a preview of Datoviz, which is a new library based on Vulkan for scientific visualization. And now we have this generous grant from CZI to work on VisPy 2, as Nicolas explained. So VisPy 2, the goal is really to make new foundations for VisPy based on more modern GPU technology like Vulkan, Metal on macOS, and the WebGPU. It's mostly the three of us, Almar, Nicolas, and I. And the main idea is really to try to decouple between two things. One is what we call the front end, so it's the user level API to do scientific visualization. So there's a lot of research because we need to review the existing APIs and see whether we need to make a new one or use existing APIs. And the important thing to understand here is that typically scientific visualization APIs have a really slow time scale of evolution, meaning that 20 years ago, the needs in terms of user exposed API were mostly similar to the ones we have now. It's scatter plots, images, meshes, volumes, right? But the backend is what we actually use to render things using the GPU. And this evolves much more quickly. There was OpenGL, DirectX, the different versions of OpenGL, Vulkan, WebGPU, and in a few years, there will be other technologies. And by decoupling the two, we could try to have a stable code base for the front end, for the API, and have various backends that can evolve faster, that implement the higher level API. And it has other advantages like modularity, testability. It's easier to test, to extend, etc. So that's really the vision for this project. And one nice byproduct of this architecture is that it might enable distributed rendering, because web-based visualization is a big need for many users now. And with such decoupled architecture, we can target this. But obviously, the main challenge is to find a common ground, a kind of intermediate layer, so that we can implement the front end on top of this intermediate layer and implement the intermediate layer on top of one or multiple backends. So that's really what we are trying to do now. We are working, we are at the stage of the specification and the experimentation with this layer. Okay, now I will talk about Datoviz more specifically, which the goal is really to have Datoviz be a backend later for VisPy 2. But right now, Datoviz is already working. So there are two branches for now, the 0.1 and 0.2. So 0.1 is basically what was released last year. It's an all-in-one scientific visualization library based on Vulkan, written in C, and with Python bindings. And the focus, still like for VisPy, it's the performance on a very large data set. It focuses mostly on 2D because that's mainly our needs, but also there's a bit of 3D support like meshes on volume. So I still work on it. I need to do a more stable release. But at the same time, I work on the next branch, the 0.2 branch of Datavis. And here the idea is really to take the existing code base and reorganize it in two parts. One is the low-level Vulkan renderer, and the other one is the higher-level scientific visualization API that is already provided by 0.1. And the main advantage of this separation is that then I can use later when VisPy 2 is ready, the low-level Vulkan renderer as a backend for VisPy 2. So Vulkan, as Nicolas said, is really complex. It's a much lower level than OpenGL. So it's much harder to learn, but it gives you a lot more control. So typically in OpenGL, you have your application that uses the OpenGL API, which is implemented in the GPU driver, basically. And now with Vulkan, a lot of the logic that was previously in the driver is now the responsibility of the application. So it's a lot more work for the application, but a lot more control and a lot more performance. It's the main motivation for this this complexity is really to let developers achieve really high performance and leveraging the latest capabilities of modern GPUs. So Vulkan is very complex. It has something like 30 abstractions that really make sense when you understand the hardware, the way GPUs are designed, but they do not make much sense when you are just interested in doing scientific visualization. And the reason for this complexity is really to achieve high performance, typically on video games. That was the main motivation. So 3D video games are a really particular type of application because they have extremely dynamic scenes. There are a lot of things that move, that change all the time, while typically the GPU data, mostly you may have big textures and it's relatively static, while more static than the scene. Whereas for scientific application, it's really different because you have largely static scenes, but possibly dynamic data. And whereas video games are all about the structure of the scene that can evolve a lot during the application. In scientific visualization, it's mostly about the data. The data is really the focus, and the structure of the scene is much more simple and static. So for these reasons, we don't need all the complexity of Vulkan. We can simplify it, and that's what I did in Datoviz. I created a light wrapper on top of Vulkan that I call VK Light, that is specifically, that focuses really on scientific visualization. So very quickly, I won't go into the details, but basically you have some functions to store data on the GPU, either in buffers or in textures, 1D, 2D, or 3D. You have ways to provide your shaders to define how you want to display things on the screen. You can record some commands for the GPU. Then you have things that are more specific for rendering on the synchronization between the CPU, between the GPU. It's very complicated, but all of this is basically abstracted away in higher level layers. And whereas you need something like 1,000 lines of code for the halo triangle in pure Vulkan, VK-Lite, you gain a factor of 4, which is okay. It's still quite complicated, but not as complicated as Vulkan. So you have VK-Lite, and on top of this, in Datoviz, I won't go into the details, but you have many stacked layers. And in the end, you can plot things like that, a simple scatter plot. And the different layers implement the ticks, the axes, the panning and zooming, and even GUIs. And that's basically the functionality that is provided by Datoviz currently. An important note, visuals are really one of the main abstraction and the main notion in VisPy and in Datoviz. The idea is really to abstract away implementation details for a given graphical elements. And it turns out that you don't need that many different types of visuals. You have markers that you see on the top right. You have segments, lines, paths, text, meshes and volumes for 3D images. And already with this small set of visuals, you can cover a lot of the use cases, like 80% perhaps. So the idea in Datoviz and VisPy is only to work hard on the implementation of these visuals and provide these visuals as black boxes to the user, who can then specify the data for the position, for the color, for the different properties of the visuals. And there's also a possibility to write custom visuals by writing new shaders if you ever need really specific needs. A note about color maps. Color maps are really important in the scientific visualization. So they are built into Datoviz. Currently, I include 150 common color maps that come from popular plotting libraries. They are all stored currently in a texture, where every pixel is basically one value for every color map. And it's convenient because you can have just one texture on the GPU and share it among all of the visuals, all of the windows in your application, and it does not take a lot of space, and you can quickly fetch values, colors from this texture. There are continuous color maps, color palettes. There are some unused space also for future color maps. Datoviz also uses another library, which is called dir-im-GUI, which is a completely independent GUI library written in C++. And the main thing with im-GUI is that it's all on the GPU. It's all implemented on the GPU. It's extremely powerful. You have many types of widgets, and it's very fast. So it's a really impressive library, very popular, because you can really create simple or complex GUIs without any external dependency. You don't need Qt or whatever. It's really all inside the canvas on the GPU. So it's integrated into Datoviz. And just a quick note about Datoviz 0.2, which is a work in progress. So as I said, the main idea is to modularize it so that I can prepare for the future renderer for VisPy 2 based on Vulkan. And you can see here a screenshot of a prototype I'm currently working on. It's a prototype of a web renderer using Datoviz and using the GPU. So the long-term idea of distributed rendering would be to try to use the browser for doing GPU visualization, and that's possible with WebGL and more recently with WebGPU. So it's really a bit like Vulkan, but really in the web browser. In the future, it might be possible to port Datoviz into the browser thanks to WebAssembly and WebGPU, but it's a long-term goal. And in the meantime, I experiment with a hybrid approach that is made possible by decoupling between the low-level and high-level APIs. And in this particular example, I have a lightweight client in HTML JavaScript. The logic is in JavaScript in the client, but there's also a server with a GPU. So the GPU is used for rendering on the server. The client sends visualization commands to the server the server does the rendering, generates a bitmap that is sent back to the browser as a PNG. So it's really a prototype, and it actually works quite well. So it might be one way to achieve a kind of hybrid distributed rendering with a bit of logic in the browser and a bit in the on the server. So next steps are really to try to get to a stable 0.1 release. There's a lot of work that still needs to be done on packaging, continuous integration, continuous build, because it's really complicated when you deal with C extensions, with the GPU code, etc. So I really need some help. And at the same time, I want to finish the 0.2 core renderer that is in good shape, so that then I can re-implement the API, the scientific visualization high-level API on top of it. And then I can work on a VisPy 2 renderer. But for that, we need to discuss more about the protocol and the intermediate layer. So thank you. That was work done in the International Brain Laboratory, funded by the Simons Foundation, Flatiron Institute, Wellcome Trust, and INCF. And thank you to my colleagues. Now Almar will talk about PyGfx.
Yes, so I'll introduce, I'll talk a bit more about WebGPU and PyGraphics. In short, WebGPU is an API to control your graphics hardware. So similar to OpenGL or Vulkan, except it's based on Vulkan, Metal, and DirectX 12. So depending on the platform that you're on, it will use either of these. So it's an abstraction over these implementations, and it's also somewhat higher level than these APIs. Basically, when Vulkan came out, people were asking, well, is there going to be a web Vulkan? And this has never happened, and there are good reasons for this. And that's because, well, first, the API is very complex, and that would be too much of a pain for JavaScript developers. But the other reason is that it's very hard to make that safe, because if you're in a browser, you need to provide an API that is safe to run, other people's code in. And the answer to that problem is basically WebGPU. But WebGPU is not only for the web, as we'll see, and actually, so PyGraphics is built on top of WebGPU, but we're not doing that because of any intentions to run on the web. So the other tool that I want to introduce is PyGraphics, and PyGraphics is a modern render engine for Python based on WebGPU. It's inspired by 3JS, and except that we have quite a bit more support for scientific visualizations. To give you a little bit of an idea, well, I think we've mentioned this already a couple of times, but if you have a simple triangle that takes like 700 or 1,000 lines of code in Vulkan, depending on the language that you write it in WebGPU, that would be about 100 lines. And in PyGraphics, that's 15 lines. So this gives you a bit of an idea about the different levels of abstraction. So some more about WebGPU. So primarily, WebGPU is a specification for a JavaScript API. However, it's also a specification for a C API. So there's also a WebGPU.h. And these two specifications are developed in parallel. And the people who develop these specifications, there are people, representatives from Mozilla, Apple, and Google in those groups. A subset of the people who are working on these specifications are also working on a reference implementation. This is called WGPU. Maybe sometimes I use the terms WGPU and WebGPU. I mix them together. They're basically the same thing. The only thing is, WGPU is basically WebGPU for the desktop. And the idea of this WGPU project is it's a Rust project, by the way. It's written in Rust, and it's the idea is that this is going to be what drives WebGPU in the Firefox browser, because it's primarily pushed by Mozilla, people from Mozilla. And but there's also like a small layer on top, and you can compile that to a dynamic library that exposes this WebGPU.h C API. And that means that other languages can bind to that library and talk to it. So one of the things that I've been working on in the past few years is a Python wrapper for WGPU. But there are also other wrappers. So there's people creating wrappers for Julia, Go, and Rust. To talk a bit more about this project, this Python wrapper, WGPU-Py, we have on the one hand, we have a Python API, obviously. And for that, we follow the WebGPU specification very closely, except, well, obviously that's a JavaScript API. So we massage it a little bit to make it more Pythonic. On the other end, we have to communicate with this library using the C API. So we're sort of stuck in between two specifications. And the interesting or the challenging part is that both of these specifications are still in development. And that can be quite challenging. And we have to, update on a regular interval. Otherwise, we will get overwhelmed by the amount of changes. And we use a mix of automated code generation and manual changes to make these updates. The other thing that WGPU-Py does is it adds GUI support. So we have support for Qt, WX, GLFW, and also for Jupyter. So you could run visualization in your Jupyter notebooks or in JupyterLab, or you can integrate the visualization in your in a Qt application, for instance. And that's handled by WGPU-Py. Well, and then this is what we built PyGraphics on top. So let's talk about PyGraphics. I already mentioned at the beginning that PyGraphics is inspired by 3JS. And if you are familiar with 3JS, you will recognize this model. This is one of the core things that we have sort of copied from 3JS. Every object in PyGraphics is has a certain position and orientation in the world, and that's defined by its transformation. So these are the world objects, and every world object can also have an arbitrary number of children. So you can create a scene graph. Every object also has a geometry. This is basically your collection that defines the intrinsic data for that object. So if we talk about a mesh, for instance, then this will contain your vertex positions, normals, maybe per vertex colors, etc. And the object also has a material, and this defines what the object looks like, so how it is rendered. And this is defined by a series of properties, for instance, a color, maybe the thickness of a line, color maps, those sort of things. But there's also different types of materials that you can associate or can attach to a certain object. For instance, in the images on the right, you can see the same mesh object. It's the same world object with the same geometry, except it's a different type of material that's applied to it. So at the top, you can see a plain material where there's no lighting effects, just a simple color. Then there's a flat shaded object, so there's lighting effects, but it's uniform over a triangle, just so you can actually see the triangles. The third is the very common approach. It uses the Phong lighting model, and there's a texture map applied to it as well. And at the bottom, we see an interesting case where we use a mesh slice material, where you see the contours of a slice through the mesh. So it's the same mesh object in all the cases, just the way that it's rendered is different by applying different materials. To show you what this looks like in code, there's an example over here. In this case, using volume rendering. So we have some volumetric data. This is just a NumPy array. We turn that into texture. And then we create two world objects. And this code is the same, except for, you create a geometry, you give it a geometry and a material, except in the first case, you give it a MIP material. So this is a specific way of rendering a volume. It's a maximum intensity projection. And that is, you can see that's at the top right. And the other one is a volume slice material. So again, it shows the volume at a specific slice in space, and that you see at the bottom right. Some other features of PyGraphics. With PyGraphics, we try to be quite a bit plug and play. So you create a scene, you add some objects to the scene, and then it gets rendered into something that looks good. So in that sense, we are quite a bit higher level, I think, than 3JS. For instance, we have built-in anti-aliasing. We have different blend modes to deal with transparent objects, which is, if you know a bit about transparency and rendering, you know that can be very challenging. We also have a very interesting picking system. So if you have let's say you have a scene with different meshes in them, you can click in the scene and know what object you clicked. But you not only get the object that was clicked, but also the face that was clicked and even the positioning within that face where the click occurred. So we have very detailed picking information. And that can be very convenient for making annotations or sort of things. And we have an event system that sort of generalizes over the different GUI toolkits. So it doesn't matter whether you're using Qt or JupyterLab, you get the same way to deal with events in PyGraphics. So to circle back to VisPy, well, PyGraphics is a render engine. The API is much higher level than Vulkan or WebGPU, but of course a plotting API is yet another, it's yet another level. It should be much easier. Compared to that, PyGraphics is still considered low level. We don't intend to add a plotting API to PyGraphics itself, but that would be another layer that goes on top. And VisPy 2 is well, a good way to do that. So the idea is indeed, Cyrille already mentioned it, and I think Nicolas as well, that we have one API that can target different backends. And that's it. Thank you.
Thanks a lot. I mean, it's very, very interesting. And I guess I'll open it up for general questions before I ask my own. So
I have a question or
go ahead,
to
Dan.
talk about. So something that we've gotten a lot of use out of because we work with these data sets that are too big to fit in system memory or GPU memory, like very, very large grayscale images that would be hundreds of gigabytes or terabytes. So we've gotten a lot of value out of NeuroGlancer, which doesn't do anything. Are you all familiar with NeuroGlancer? It's basically it uses older, I guess, whatever's the current standard web GPU interface, but it just lets you.
WebGL2.
Yeah, it's WebGL2. It's not doing anything too fancy on the GPU, but what it does and does a very good job of is managing chunks of a really, really big data set, basically scheduling what gets in CPU memory, what ends up in GPU memory, registering callbacks based on where the user is, how much the user has zoomed in, with the end goal of just providing like a smooth and seamless way of browsing these really, really big data sets. So I think on the GPU end, it's not as complicated as something like volume rendering. You're just rendering a 2D slice through some volume that's living on GPU memory. But do you know of anyone who's using any of these tools to implement something like that? Because we would love more things that give us what NeuroGlancer gives us. Like a diversity of tools that can offer the same experience would be great.
So guys, at least for the very large data set, but Cyrille can speak about that. So there is some option, for example, for remote rendering to make sure that the data are close to the GPU just to avoid the transfer. And for the very, very large image, I think it's, we didn't talk about that yet. So in VisPy, I think there are some examples to do that. But if it's very large, I don't know to what extent we. So we know so it depends of course, of your data, but in any case, you are limited by the number of pixels you can show on the screen. So it doesn't make sense to upload all your data on the GPU. So you want to do the just-in-time transfer, but at this point we didn't talk about that. But we need to take this into account for sure.
Yeah, at least in Datoviz, the reason why I said that typically in scientific visualization application you need dynamic data is precisely this kind of use case where you need to efficiently and quickly upload new chunks of data as you continuously zoom in on the pan. So that's really a use case, but all of the logic to choose which chunk you are, currently it's not part of Datoviz. It might be part of the higher level of VisPy 2. We need to talk about that, but if it's not, then we will make sure to provide the facilities in VisPy 2 to let you easily and quickly upload new chunks of data in the GPU. That's really an important use case here.
Okay. Any other questions from the general audience? So I had a question about, you know, I wasn't quite understanding with the VisPy 2 level, and then you have a number of these backends, including the PyGfx, the Datoviz, et cetera. And then there was also this notion that you want to have some sort of an intermediate API, some sort of scientific visualization API that kind of obscures all of this issues with Metal, Vulkan, D3D, you know, you name it, WebGPU. How do you think that your viewpoint of this compares to, I don't know if you had a chance to look at Inari, you know, and the Kronos sort of look at this, where they're obviously trying to create a scientific visualization API that does pretty much that, right? Does an abstraction layer over all of the potential backend rendering. How would your stuff relate to Inari?
Yeah, it's quite close. I was quite interested in seeing the presentation of Inari. There are many ideas that are similar, but one big difference is that I think they really focus on 3D, on a really complex 3D visualization, whereas at least myself and in Datoviz, I really focus on 2D and high quality 2D visuals, and that's actually very, very hard and not that common in scientific visualization on the GPU to do. We didn't talk about this, but it's very complex to draw, for example, a nice anti-aliased path on the GPU. You need to triangulate it. You need a custom fragment shader to compute the value of the alpha transparency depending on the distance between the median and the boundary of the path. Text is also quite complicated. So all of this, I don't think it's part of an array because they focus on 3D where it's really meshes and volumes and things like that. So that's one big difference. Perhaps Nicolas and Almar.
I think this is one of the problems we had with the time of VisPy. So since you have the GPU, there is a lot of 3D library for scientific visualization. But at that time, there were mostly nothing for like regular 2D, where you have a large data set and you want to achieve a high quality. And I think it will be the same with this new library. So it will be, of course, it will be very useful for complex 3D rendering, for any kind of volume. But for, let's say, intermediate stuff, you don't have so many libraries. So there are some in using only CPU, which are fine, like the anti-grain geometry library, but it does not take advantage of GPU. There were some effort by NVIDIA for 2D, and even with the Kronos group for defining a 2D API taking advantage of the GPU, but it never materialized in any library. And so in the end, we are 10 years after the first release of VisPy, we still don't have this, let's say, basic library to do proper 2D rendering and 3D with a simple API, because our public is mostly the scientists. So of course, they don't want to deal with the methods, so with a GPU or Vulkan or anything, but they still want some freedom such that you can build on top of that, like an array. It's what they did with VisPy. And so the idea is really to have this foundation for simple libraries that will take care of all the gory details of talking to the GPU, and people will build on top of this. And unfortunately, I don't think there are such libraries. I don't know why, because maybe it's not, I don't know, maybe people think this is not interesting, but there are really a lot of people that are interested in that stuff.
For me, so my use cases are mostly medical visualizations, like 3D visualization of CT scans and MRIs. And I remember that, like, we watched those videos from Manari a couple of weeks ago, and I remember that we thought, well, it's very interesting, but it's not, we cannot really make use of it. But I can't recall the exact details why that was, to be honest. Yeah, I think it's already too. I think we're looking for more control to have very specific visualizations for very specific scientific use cases, and it looked like that would be hard to do in Anari because it's already geared towards certain visualizations.
Yeah, perhaps we can say Anari is slightly higher level than what we target, because it's really meshes and volumes as far as I understand. Whereas we try to be a bit more abstract in the kinds of visuals we want to support.
Yeah, I think that makes a lot of sense. So when I was looking at Anari as well, it looked like it was geared toward, they wanted to make things very simple for certain kinds of visualizations, but unless you actually had a renderer that would provide sort of an escape clause, so that if you wanted more lower level features or various other things, then it would depend on you getting a renderer that happened to meet the Anari specification. And so an example of this would be, like if I wanted to do sparse volume rendering using nano VDB or one of the, the newer sparse volume representations, that wouldn't actually be represented in a current, like you'd have to convince a renderer developer to actually introduce that, and then it would be exposed through some sort of ability to say, okay, this is now available in my renderer and I can make use of it now on the other side. I mean, it's also interesting too, there's like the 2D versus the 3D emphasis as well that you were talking about, Cyrille. So that point is well taken. And I think partly it's because now that they have the ray tracing cores, right, and all this really nice hardware, that maybe some of the emphasis might be going toward exploiting that. So I had another question about, and this probably goes more to Almar, about when you were talking about the WebGPU, WGPU, and how it's still kind of rapidly, it's still in a state of flux. When do you see that kind of dying down, such that for people that don't want to necessarily be messing with things that are constantly changing under them, that it would be a good time to actually start stepping in and examining the technology to sort of build on it?
I don't know. I don't have a straight answer to that, because
Is there a roadmap that with some kind of goalposts that might?
I don't think they have like milestones for the far future. It probably depends on how things progress and things like that. I know that they're still having meetings and progressing, but I don't think they have like set dates that they want to settle things down. Obviously, at some point they'll have to say, well, we have a certain 1.0 release. This is WebGPU. But once they say that, they have to make sure that it remains backward compatible because it's the web, right? So it will probably take a while before they actually do that. What I can say is that as things are progressing, the changes that are being made are more incremental, smaller changes instead of really big changes that affect the API a lot. So if you target like WGPU Pi, for instance, then there will be quite a bit of changes every time that I decide to to synchronize the API. But if you use PyGraphics, then most of the changes in PyGraphics will actually be under the hood, so you won't notice anything. Yeah. So if you are on that level, if PyGraphics is a low level enough for you, then that should be relatively safe.
On a somewhat related question, so there's the WebGPU, the WGPU, the Rust implementation of that, and you're building on top of that in order to get to Python. I guess my question would be, like, normally when we think about like hardcore graphics programming, right? You talk about people that really want to start sticking with C++ or one of the lower level languages, a lot of control over the memory, everything else like that, make it very tight and efficient. When you were examining how you might use WGPU and the fact that it's written in Rust, were you thinking about perhaps writing 3JS equivalent in Rust and then writing a layer on Python on top of that? Or was it just that, no, okay.
So my experience with Rust is, well, I did a bit of Rust before I started. I made a few contributions to like the top layer of WGPU, so the part that creates the C API. But it's not a language. Once you have it finished and the compiler says it's good, then it's fine. But it's not really a great language to do scientific stuff in because it's the progress is too slow. At least that's my opinion. So I wanted to stay in Python land, and I also, so to come to the other question, it's a deliberate choice to make the render engine in Python because that makes it hackable. That makes that people can easily create their own, types of word object. They can create their own shaders, their own materials, and that makes it super interesting because you can create really weird visualizations if you want to using that system.
That's cool. Okay.
I have a question about browsers. Like, the relationship between Python and the browser is kind of interesting because you have Jupyter notebooks, which are a browser-based tool, but the Python itself is not running in the browser. And then there's the whole way people visualize stuff when they're using a Jupyter notebook, which is typically something gets turned into a PNG or a JPEG, or they fire up another browser tab and look at bokeh or some other web plotting library. So how do you see like high performance visualization and Python and the browser, how do you see that looking in 5 years?
You have to keep an eye on Peter Wang because I know that he has ideas for this. So that's one. There might be at some point people actually bringing Python to the browser in a more, proper way. And I remember like back in when we started VisPy, I remember at the time I also worked on bokeh for a while, and I was really in sort of a split because I really liked the web and I really liked 3D visualization, but it seemed like you cannot have both. You either use Python or the web, but I've sort of learned to live with the fact that if you want to have Python, then the Python part is doing the rendering, and if you want to see that in the browser, then you ship the PNG to the browser, and yeah.
I haven't followed closely, but there's a lot of work right now around the PyUDI project. I just put a link in the chat. Some of you might know, to port CPython and NumPy and a lot of Python extension that I use in scientific computing into the web, into the browser with WebAssembly. So that's quite interesting. And since we have WebGPU, we can hope maybe in 5 years to have some kind of high performance visualization in Python in the browser with WebGPU. That's really a hope, but that's really long term.
Okay, great. Are there any other questions? If not, could I get the speakers just to remain behind a bit, and we'll end the talk. Thank you very much for presenting very, very interesting stuff.
Thank you.
I actually do have a question.
I
think you mentioned.
Okay, Mark.
Yes.
Go ahead.
So earlier, I think you kind of proposed a strategy of creating a common API with multiple backends. I was wondering if the backends were intended to be also directly accessible as well, if someone wanted advanced functionality from a particular rendering engine or rendering language. So.
Yeah, I think it might be a decision to take on a backend by backend basis, but at least for Datoviz, yes, I always plan to offer some kind of API to the user, for the experienced user who want more control, who want to write custom shaders, who don't want to go through the VisPy protocol. So for Datoviz, that will always be a possibility.
Yeah, I think this is the idea. Even with the VisPy API is just the lowest level, and people will be able to build whatever they want. If you want to build Matplotlib on top of this, you can. If you want to go for Vega or Decoupled, but very, very high level, the idea is at least to provide this necessary lower level.